Hello and good morning, evening, or afternoon, depending on what time it is. I'm going to be talking about the volumes of things. I'm reading all of this off of the PowerPoint, and I'll link it in the video description / in my project, so you should be able to see it. Now, the first thing I'm going to talk to you about is cross-sections. So I created my model by creating a graph of a natural log. I then split that graph into 11 sections, each the width of my cardboard piece, which is around like a quarter-ish of an inch. I then created half circles using the length of each cross-section. In order to find the area, I simply added up the volume of each cross-section. My result was 53.6 centimeters cubed. Now, following this very practical way of solving this, measuring the actual material, we are now going to use the theoretical way of solving this, calculus. So what we're going to do is we're going to take the integral of the equation, the base, and use the cross-section's volume, pi r squared, divided by 2, as our x. And then once we plug that in, we get 53.5. Now, of course, this is really close. This is a 0.1 centimeter difference, so pretty reliable. Now, which is better, cross-sections or calculus? And it depends on what you're trying to do. If you're actually trying to make something out of sheets of solid material, cross-sections mimic that behavior more accurately. But if you're using a smooth surface, or if you're carving something out of a solid object, calculus serves you better because it is inherently more precise. It focuses on things to a much finer degree. So yeah. The second thing I'm going to talk to you about is solids of revolutions. Now, I have a picture here. You'll be able to see it in the slide. To calculate the volume of this one, I used the simple left-hand, right-hand approximation, and I have my spreadsheet there that shows you how I did that. Now, to come up with this volume, we will add several integrals together. Take the integrals, plugging in pi r squared again for x in order to get the full volume. And this time I'm not dividing it 2 by 2 because I'm not doing half circles. I'm doing the full circle. So that's why I do that. And again, once I added all of my integrals together, I get 100.9 centimeters cubed. And in this case, integrals are by far the best measure for one basic reason. My graph is an approximation of a thermos. If I was using cross-sections, or left-right hand approximations, I would be making an approximation of an approximation. So it's going to be incredibly imprecise. So yeah, so it's just simply not the right way of doing it. So in conclusion, as we can see, my results were pretty close to my actual results. What I mean by that is my calculus, the theoretical, were pretty close to the practical. Now, keep in mind my actual results are approximations in and of themselves, so they're not 100% accurate. But that wraps up my project. This is Volumes of Things. Thank you very much.